Okay, cool. So we're live. Well, welcome everyone to another TCS Plus talk. We're very lucky to have Jasper Lee. He'll tell us about optimal sub-Gaussian mean estimation in R. And before we get started, let me just say a few things. First of all, just to thank the rest of the organizers, which include Clement Knon, Rachel Cummings, Anindya Day, Sumega Garg, Gautam Kamath, Ilya Rajenstein, Oded Regev, Salil Shram, Noah Stevens-Davidowitz, Tomas Vidik, and David Weiss. And I'll mention that I think 2 weeks from now, we're trying to have another talk where Andrea Lincoln from UC Berkeley will tell us about fine-grained complexity, but we still need to finalize the schedule, so we'll probably send an email out about that. So Jasper agreed, so please feel free to unmute yourself and ask any questions throughout the talk. I'll also be monitoring the chat. But I do want to encourage people to keep their camera on and give Jasper some visual feedback. But with that said, so yeah, please, Jasper, go ahead.
Great. I thank the organizers for inviting me here. Today I'll be talking about estimating the mean of a real value distribution, which is a very basic problem. So what am I talking about? I'll start by let me start by giving you a very precise formulation of what the problem is. Oh, and this is joint work with Paul Valiant. So the problem is, as you would expect. So let's suppose we have some unknown distribution D over the real numbers, and we get sample access. We get IID sample access from the distribution. And the goal is to estimate the mean of the distribution to some additive error epsilon, failing with probability at most delta. We want to find an estimator to do that. And the goal, of course, is to minimize the sample complexity, namely the number of samples we need in order to satisfy this epsilon delta guarantee about for this mean estimation problem. So this is a very standard hack-like high probability-like formulation of the mean estimation problem. And this is obviously something that underlies much of statistics, but in case you don't really care about statistics, if you're really only focusing on algorithms, this is also a tool that we frequently use in designing, for example, various kinds of randomized algorithms as well. So super fundamental problem. The question you might have in your mind right now is there actually a problem to be solved? Don't we already know how to solve it? So for the talk, as an outline, first I want to convince you that there is actually a problem to be solved. There is something non-trivial going on. I also want to talk to you about exactly how we formulate the question before I state our main result and the algorithm. And I will also want to give you some intuition about why our algorithm deserves to work. Before going into some of the more interesting analysis techniques we need to employ in order to analyze our estimator. So let me start by answering your question. Don't we already know how to solve mean estimation? Like the conventional thing to do is to take the sample mean, namely that you get a bunch of samples, you sum them up and divide by n, right? So that's the most basic mean estimator that we are all familiar with. So the first thing I will say is that the sample mean is actually not optimal, not even in one dimension. So it's in fact not even close to optimal. So the sample mean does have a lot of good properties. For example, it is optimal for Gaussians, for example, in various senses. It's also a pretty good streaming algorithm. It's somewhat robust to correlations in your samples as well. On the other hand, as soon as we go away from Gaussians to distributions with heavier tails than Gaussians, then the sample mean gets like pretty bad pretty rapidly, quickly. Now, you might be wondering, what about all these tail bounds we learn about, let's say in our first class in randomized algorithms? Like we get all these like Chernoff bounds, Hoeffding bounds, and so on. So how does what I'm saying mesh with all that? So let me give you a couple of examples of what happens when we actually use tail bounds, apply tail bounds and see what kind of sample complexity we get from these tail bounds. So the first example is, let's say we assume that the distribution does have Sub-Gaussian tails. So it does have Sub-Gaussian tails. Then if we apply the corresponding tail bound, the sample complexity you get is this expression right here. So sigma squared is the underlying variance of the distribution, which is unknown. So some underlying variance of the distribution. And again, epsilon is the additive error we want to estimate the mean to. and delta is the failure probability. So this expression here is the sample complexity for the sample mean with respect to Sub-Gaussian distributions. But Sub-Gaussianity is a really strong assumption. So let's apply other kinds of concentration inequalities and see what happens. So another example I want to show you is using Bernstein's inequality, which makes the assumption that the distribution is bounded, let's say, between negative 10,000 and 10,000, so some constant width interval. So in that case, when we apply Bernstein's inequality, we solve it, and then we get this sample complexity. And crucially, there's this additive term of 1 over epsilon times log 1 over delta, which is like necessary here. In particular, if the variance of the underlying distribution is smaller than epsilon, then this second term actually dominates. So this is actually a distinct sample complexity from the first one. So as we apply more and more tail bounds, what's going to happen is that we need to make all sorts of different kinds of assumptions, and then we get all sorts of different kinds of sample complexities. So if you apply like a smell test to the whole thing, there's something fishy going on. And in fact, as I mentioned, the sample mean isn't even close to being optimal in the following sense, that we know the Chebyshev's inequality is actually tight. You can write it down using like examples, like even just Bernoulli coins. So Chebyshev's inequality is tight, meaning that the sample mean, the sample complexity of it is going to be at least this expression here. So the thing I want to draw your attention to is the dependence on the failure probability. The sample mean has inverse linear sample complexity dependence on the failure probability, this 1 over delta term, as opposed to the more conventional log 1 over delta term. So the sample mean is exponentially slower than what we would hope to get from tail bounds, essentially. So the sample mean is really, really bad in the high probability regime. So hopefully at this point, I've convinced you that the sample mean doesn't work. So now the question is, so what does work, or rather, what is our goal even? Okay, so to see what the goal is, let's go back to the Gaussian special case. Why Gaussians? Because Gaussians tend to be the edge cases of many statistical problems. So we want to estimate the mean of a Gaussian. So you know for a fact that the underlying distribution is going to be a Gaussian. So what is the sample complexity of that? Turns out that is really well understood. So for the upper bound, as I mentioned, the sample mean is optimal. So if you do some calculations, the sample complexity to estimate the mean of a Gaussian is this expression. So this thing here we saw on the previous slide, we have this constant of 2. It turns out we can actually calculate this constant of 2. So instead of hiding it in the big O notation, we know what the constant is. And correspondingly, this is also tight in the sense that this constant of 2, even the constant of 2 is tight. So this sample complexity lower bound comes from the fact that it's very hard to distinguish 2 Gaussians of the same variance, but of slightly different means. So if you look at like a diagram like this, so two very similar Gaussians, trying to distinguish between these 2 Gaussians, it turns out it requires this number of samples in order to do that. Okay, so in the Gaussian case, we essentially have a complete understanding of what the sample complexity is, up to this 1 plus little 1 term. So we even know that the complexity has this right constant of 2 in the Gaussian case, which motivates the question of, is it then possible to somehow find a mean estimator that has this sample complexity, this Gaussian sample complexity, with the right constant of 2, but it works not only for Gaussians, but for all distributions with finite variance. So we want to completely generalize this to all distributions with finite variance.
So Jasper, there's a question here in the chat from HCDU. Cool. He's asking if the sample complexity is known for a Poisson distribution. I'm guessing the
for the sample mean, you mean?
Yes.
Right. So yeah, so I mean there are tail bounds for the Poisson distribution. Actually, Clement, one of the organizers, he wrote up a note on the concentration of the Poisson distribution. So yes, it's understood, and the Poisson has heavier tail than the Gaussian, so it wouldn't be this sample complexity essentially. It's got a different tail. I hope that answers the question. Yeah. So yeah. Great. Okay. So yeah, let me move on. So, right, the goal again is to find a mean estimator with exactly the sample complexity for all finite variance distributions. So at this point, it might be, it's a good point for me to tell you about what the previous work has been. Catoni, in his 2012 paper, basically reinvigorated this whole line of work of really trying to understand the basic problem of mean estimation. And he showed that you can actually achieve the sample complexity with the right constant of 2, assuming you know what the variance is. If you know exactly what it is, or if you know it to incredibly high accuracy. He also generalized this along with a different work by Devroy et al. They generalized it to the case where, let's say you know that the distribution not only has finite variance, but has finite fourth moment. And not only is it finite, but also it's bounded by some absolute constant. In that case, essentially the observation is that you can use the fourth moment, the finiteness of the fourth moment, to estimate the variance to high accuracy, and then basically plug it back into this estimator, and then you can get a very good accurate estimate of the mean as well. So our work, crucially, we don't need to make any of these assumptions. So we only assume that the variance is finite, but is actually unknown. Now you might also be wondering, what if we don't care about this constant of 2? What if we only want big O tightness? So in that case, actually, we've known how to do this for decades. It's a very standard result that's been discovered and rediscovered. That is the median means estimator. I believe at least the best constant I've seen is instead of a 2, it's got a 32 here. So we're off by a factor of 16, let's say. Right, so this is basically the line of work that is leading up to the current work. Now, the other thing I want to say on this slide before I move on to our main result is we're making an assumption that the distribution has a finite variance, which might sound a little bit strange if I don't explain it. So why this finite variance assumption? So let me divide it into 2 parts. So what if, let's say, we assume that the distribution has finite 100th moment? Does that help the problem? The answer is no, because the Gaussian lower bound that I was alluding to earlier in the talk, Gaussians, of course, have finite all moments. So even if you assume a finite 100th moment, that's not going to help the sample complexity. Now, on the other hand, what if you assume a weaker moment assumption? So instead of having a finite variance, what if the distribution only has a finite 1.5th moment? So maybe the tail is decaying much slower than you would like. So it turns out that, okay, so there are 2 answers to that question. So what happens then? First thing is the sample complexity no longer makes sense because it depends on the variance. So, and the variance is undefined in that case. But the second answer, a more interesting answer, is that it turns out the dependence on the additive error is not going to be as mild as 1 over epsilon squared. It's going to be a larger exponent as you make smaller and smaller moment assumptions. So in this sense, sort of carving out the problem with the second moment assumption is the right thing to do. So that is the framing of the problem. Let me pause briefly if there are any questions.
So this standard result of the median of means, saying for any distribution with bounded variance, this estimator uses 32 times this quantity.
Yeah. So what we're really trying to do is optimize this constant right here. This is the point of the work, and we have a pretty easy to implement estimator as well. So yeah, so let me now go to the main result. So as I promised, the main result is that we do have an estimator with this Gaussian sample complexity. And furthermore, the estimator computes in linear time, linear in the number of samples. The computation aspect, I'm not going to say much about it for this talk. I want to focus on the statistical part. So one thing you might be wondering about at this point is that the sample complexity depends on this unknown parameter. So I mentioned that our estimator works for every finite variance distribution, but the variance doesn't even need to be known to the algorithm. So you might be wondering, so when do we stop, right? So this formulation of the problem, we're basically asking, once you fix the additive error and once you fix the failure probability, what's the minimum number of samples? But you can actually change the parameterization. A more useful way to parameterize the problem would be, let's say you fix some amount of data, and then you fix a failure probability, and then you ask, what's the smallest additive error you're going to get? What's the convergence rate of the estimator? And that's a kind of a more useful way to formulate the theorem. And that is exactly what we actually do in the paper. So once you fix a number of samples, and then you fix a failure probability, we are able to bound the additive error by this expression, this complicated expression right here. You don't need to know exactly what the expression is, so don't worry for the rest of the talk. Just that this is a more useful way to actually use the theorem, to use the estimator. Now, without further ado, let me actually give you the estimator, which fits on this slide. This is going to be a little bit opaque for now. So let me first state and describe the estimator before explaining and giving you intuition about what one is actually doing. So as input, as I mentioned, we get n samples from our underlying distribution, and then we fix some failure probability delta. The first thing we're going to do is compute the median means estimate as a preliminary estimate. So the median means estimator from previous one. So once we have a preliminary estimate, we are going to solve for this parameter alpha in this equation. For now, if you're worried about computational issues, just note that this equation, the left-hand side is a piecewise linear function in alpha and is increasing as well as monotonic. So there's structure that allows us to solve for this alpha parameter. Now, once we solve for this alpha parameter, all we need to do is plug it into this expression here, which is just a sum, and then evaluate this entire expression and return our final estimate mu hat. Okay, so this is the estimator. This is the entire estimator. I've dumped these two equations at you. The question is, what do they actually mean? So let me spend a bit of time explaining what this estimator is actually doing. Okay. So yeah, now what I want to do is to help you interpret what the estimator is doing and justify some of the constructions at least. So in order to really understand what's going on with the estimator, it helps to simplify the notation a little bit. So let's write down some simplifying assumptions that doesn't really change the problem. So just to recall, the estimator is first you compute some preliminary estimate of the distribution, and then you solve for alpha in this first equation, and then plug it in to compute the final estimate mu hat. One of the first basic properties of the estimator we can write down, pretty easy to check, is that the shift and scale invariant in the following sense. If you try to shift all your samples by some amount and scale the samples by some amount, then the output estimate is going to shift and scale by exactly the same amount as well. Which means that to analyze and understand the estimator, it suffices to only look at distributions with mean 0 and variance 1. Okay, it's just to basically normalize everything. Now, a second property, as I mentioned before, this estimator is essentially taking a preliminary estimate and then outputting a final estimate. If we now treat this estimator as a function of the preliminary estimate, we can actually show that it's very insensitive to what the preliminary estimate is to begin with. Now, combined with the fact that the median means estimate is actually very good to begin with. So recall that this is a big O optimal estimate to begin with. We might as well pretend that the preliminary estimate is equal to the true mean because it's very insensitive, right? So the final output is very insensitive to it. So we might as well pretend that our very accurate thing is actually the true mean, which by the previous assumption is equal to 0, which lets me simplify the estimator, the equations, to something that's slightly more palatable right here. Okay. Now, given this, what is the estimator actually doing? Let me draw your attention to this second equation, which is actually computing the estimator. Now, ignore this 1 minus something, 1 minus min term. This is just the sample mean, right? So what the estimator is actually doing is subtracting some weight from each of the samples before computing the sample mean. Now, how do we subtract? How do we decide what weight to subtract from each sample? The way we're going to do it is that we're going to subtract a total of 1/3 log 1 over delta much weight from all the samples combined. And the way we distribute this weight is we're going to distribute it proportionate to the sample's square distance from the true mean. That's what the square means. The min with 1 is basically saying that we will never subtract more than the entirety of the sample before we compute the sample mean. So hopefully this is a more discrete, more combinatorial interpretation of what our estimator is doing. Does that make sense so far? Great, okay. So yeah, so this is a more combinatorial interpretation of what the estimator is doing. Now, perhaps the most unnatural thing about the estimator is this magic number of 1/3 log 1 over delta. So let me spend another slide convincing you that that's actually the right thing, or to see where 1/3 log 1 over delta can fall out from a very simple example. So to see why this magic number, it turns out we can already derive it from the very simple example of Bernoulli coins. So if the underlying distribution is just a Bernoulli coin. So consider doing n flips of some Bernoulli coin of bias p. And the interesting regime is when the bias p is very, very small. So it's an extremely rare coin, okay? So what we care about is, let's say, the number of heads. And in the limit, because of this very rare coin regime, the number of heads is distributed as a Poisson distribution with the parameter that is equal to the product n times p, okay? And the sample mean would basically just return number of heads divided by n. Now, on the right here, I've taken the liberty to choose lambda equals 100, and I've plotted the log PDF of the Poisson as this blue dash curve right here, okay? And as you might recall, we are trying to compare the performance of our distribution to the corresponding Gaussian. So I've also plotted the solid curve, which is the logarithm of the Gaussian with matching mean and variance. And of course, the two distributions are different. So we're somehow trying to get this Poisson to behave like the Gaussian in some sense, in order to achieve some Gaussian performance. Now, the tail we're worried about is this right tail here. So the Poisson distribution is known to have heavier tail than the Gaussian in the right tail. So it has more probability that the estimate is going to be too much bigger than the true mean of 100. So this right tail here. So we need to somehow change or correct the Poisson into the Gaussian. So the question is, in what sense are we trying to correct the Poisson into the Gaussian? So the way we're going to do that is to look at the delta tail of the two distributions. So like this. So by delta tail, I mean the point after which there's delta probability mass in both distributions. Now it turns out that this gap right here is going to be exactly 1/3 log 1 over delta. So the way we're going to change the Poisson to correct the Poisson into a Gaussian is to basically shift the whole Poisson curve to the left, just like that, which in the sense of the estimator, that means we're going to subtract 1/3 log 1 over delta many hits before computing the sample mean. And that turns out to be the exactly right thing to do. So even from this very basic Bernoulli coin case, that motivates why we're subtracting 1/3 log 1 over delta samples total in weight anyway. So I think, yeah, that for time's sake, that's what I want to say about the estimator. If there are any questions.
So is it going to matter that the original estimator was the median of means, or can it be some arbitrary one with like bad constant, and you can improve the constant factor?
For the higher level, yeah, it doesn't really matter. In fact, you can even use the sample mean as the preliminary estimate, but then apply the last two steps many times to get it to converge. That will also work. But it's just it's a simple presentation of the estimator. You just start off with something you know is pretty good, and then you do one step of this iteration of refining the estimate. But yeah, so anyway, so this is what our estimator is doing. So now I want to tell you about the analysis, which I think is also a very interesting part of this work. So reminder, again, our estimator is solve for alpha in the first equation and then plug it in and output this mu hat in the second equation. So recall that our main theorem is essentially trying to prove a tail bound. We're saying that our estimator cannot exceed some quantity by with too high probability. So it makes sense that the highest level approach is to try to derive our own custom Chernoff bounds, our own tail bounds for this particular estimator. And just a reminder, what I mean by a Chernoff bound, I mean a bound of this form. So the probability that a random variable exceeds some quantity is bounded by its moment generating function evaluated at some parameter divided by e to the t epsilon. So this is the vanilla Chernoff bound, something like this. But we quickly run into two major issues if we try this approach. And for the rest of the talk, what I want to do is to give you solutions to these two main obstacles. So the first obstacle is that we need to somehow control this moment generating function of the estimator. But the issue here is that moment generating functions are only easy to control if your estimator is a sum of independent terms, which unfortunately is not the case for our estimator. So to see that, let's look at the second equation again. So this second equation, if we fixed alpha to be a constant, then we have a sum of independent terms. Then each of the terms is only going to depend on a single sample. Unfortunately, in this particular scenario, this alpha parameter comes from the first equation. It's the solution to the first equation, which involves all the different samples. So this alpha is introducing dependency between all the different terms in the sum. So we have sum of dependent terms for our estimator. So the question is, how do we then somehow try to do a Chernoff analysis which requires handling things like moment generating functions? So this is the first main obstacle that I'll be discussing for the rest of the talk. The second obstacle is that, let's say we even get around this issue of independence. Once we get something that is actually independent, we still need to analyze the estimator for over a very large space of distributions. In particular, all distributions with mean zero and variance 1. Now, usually for other kinds of tail bounds, you need to make much stronger assumptions. For example, Sub-Gaussianity or bounded support and things like that. Here we're optimizing, we're trying to bound the tail probability for all variance 1 mean zero distributions. So it's a very large space. How do we deal with that? That's the second main obstacle. So I hope that the solutions to these two obstacles that I'm going to present to you, I think they're going to form a somewhat generalizable framework that might be useful for doing other kinds of statistical tasks as well, which is why I'm presenting these two solutions to you. So let me give you an outline of the two main steps we're going to do for the analysis part of the talk. So the first obstacle is that we get this sum of dependent terms. So what we're going to do instead is we're going to reduce the main theorem to finding proxies of the estimator that are actually sum of independent terms. So once we have these sums of independent terms, we're going to prove Chernoff bounds about these proxies instead. So we aren't going to directly analyze the estimator, but we're going to find proxies of the estimator and then analyze those instead. Once we do that, we're going to simplify the Chernoff bound analysis using optimization techniques, in particular duality techniques, linear programming duality and max-min duality, essentially. Once we do these two steps, what is going to remain is proving a very strange inequality that is not going to be part of this talk because neither Paul and I actually found much insights in that inequality part of the analysis. So yeah, there's a question. So would it be fair to say that your new estimator is a weighted mean of sorts where these weights are meant to penalize points further away from the mean? Yes, that is completely fair. But the trick is to find exactly how we're going to penalize the samples. That turns out to be rather delicate in order to get the right sample complexity, including the constant. There are other works, including where you are a little bit less careful, I guess. You just do some thresholding and then you discard all the samples away from beyond a certain threshold. That's called a trim mean estimator. That is only big O type and not like constant type. And then the second part of the question is, additionally, the full weight has been shrunk to account for deviations from a Gaussian. Yes, that is pretty much what's going on. Maybe I can say a little bit about that at the end of the talk. Let me defer it to the end of the talk, or maybe we can talk about that offline as well. But the short answer is yes. Okay, so yeah, let me continue. So again, the two steps I'm going to present to you are finding proxies of the estimator such that we could do Chernoff bounds on them because they will be sums of independent terms. And then for the actual Chernoff bound analysis, we're going to use duality techniques to drastically simplify the Chernoff bound analysis. So let me dive into it. And this second half of the talk is going to be a little bit more technical. So the first thing we're going to do to find these proxies of the estimator, this part is essentially trying to rewrite the estimator into a different form. So recall again our estimator, which is solving for alpha in this first equation and plug it in to solve for this final estimate mu hat. So I claim that this estimator could be presented in a form of what is called a psi estimator in the area of robust statistics. So I claim that the estimator is equivalent to solving for mu hat and alpha in these, such that these two equations both equal to 0. So it's a root finding problem. To see that's actually not hard to see, because this first function is really just the left-hand side subtracting the right-hand side of the second equation. And similarly, the second function is just this thing, is just the left-hand side subtracting the right-hand side in this first equation. Okay, so obviously the right solutions, mu hat and alpha, is going to be the zeros of these two functions. Now you might be thinking, why are we doing something that sounds so trivial? The point here is that if we fix mu hat and alpha to be constants, both these functions, both these sums are sums of independent terms. So we're making a little bit of progress towards finding our proxies. Now that I've rewritten what the estimator is doing as a psi estimator, it helps to reformulate what it means for the estimator to succeed, what it means for the psi estimator to return something that is a good estimate. So for that, I have this following lemma, that the following three statements are going to be equivalent. So the first statement is the vanilla statement saying that our estimator returns a mu hat estimate that is good in the sense that is less than epsilon away from the true mean of 0. So this is the vanilla statement. Now I claim if we try to shift it to the psi estimator language, we get the following statement. So that is equivalent to saying that for every pair mu hat and alpha of bad candidate solutions, by bad candidate solutions, I mean mu hat that is too far away from the true mean. For every such pair, it must be the case that one of these functions have to evaluate to non-zero. Because otherwise, we would have solved for this particular pair of mu hat and alpha and then returned the bad mu hat. Right, so this is a completely equivalent statement to the first equation. First statement. But this statement isn't very palatable. Like this involves disequalities and also a disjunction. This isn't like an inequality that we can reason about. So let me rephrase the second statement just a little bit more to give the following statement. So again, for all candidate pairs of solutions, mu hat and alpha, such that mu hat is a bad solution, so it's too far away from the true mean, then it must be the case that there exists some coefficients such that this inequality is true. So the linear combination of the two psi functions must be bigger than 0. So that's just a reformulation of this second statement here. Now, you might be wondering, why are we doing this inequality? So the reason is that once we fix d mu and d alpha to be constants, then we've basically combined two independent sums of independent terms into a single sum of independent terms. So that's going to end up being our proxy that we're going to analyze, essentially. So with this lemma, we can now reformulate the main theorem to the following form. So again, our estimator is solve for mu hat and alpha such that these two functions equal to 0. Then our reformulation of the main theorem says that for any bad pair of solutions, it must be the case that there exists two coefficients such that the linear combination is bigger than 0. This is now the new main theorem we're trying to prove. And you might be wondering, okay, now it sounds like we've reached the point we can use a Chernoff bound to prove this, but not quite actually, because of the quantifier form of the statement. In particular, the logical quantifier form of this current statement has a probability outside with some quantifiers inside. So for all bad pairs, there exists some coefficient such that some inequality is true, and we want to bound the probability of this event happening. But a Chernoff bound only allows us to prove probability of events without any quantification. So the natural way to turn this into something that we can finally use a Chernoff bound analysis for is to somehow yank out these two quantifiers out. So that gives me the following lemma, which says that for our psi estimator, it must be the case that for all bad pairs of solution, there exists coefficients such that over high probability over our sample set, this linear combination is bigger than 0. This is now something we can actually prove with a Chernoff bound. In particular, this left-hand side here is a sum of independent terms, which is the proxy that I was talking about that allows us to do a Chernoff bound analysis. So to go from the lemma back to the main theorem, it's a very standard discretization plus union bound kind of analysis. So I'm not going to go into that. And yeah, again, this is something we can prove a Chernoff bound for. And we found these proxies that we know how to analyze, or we will know how to analyze rather. Does that make sense? So I've done a bit of rewriting of the estimator, essentially. It's a little bit notational, but it turns out there is a way to rewrite the estimator in a way such that we get a lot of independence out of the estimator. And that's what allows us to analyze what's going on with this estimator. Are there any questions? Great. So what we've done is complete this first step. I've reduced proving the main theorem to proving Chernoff bounds on proxies of the estimator. Okay, now the second part is how do we actually do the Chernoff bound analysis? How do we prove the previous lemma? This is the remaining part of the talk. And we're going to use duality techniques in order to really simplify the Chernoff bound analysis. So recall this lemma again. Consider an arbitrary mean zero variance 1 distribution. For all pairs of bad solutions, there's this existential quantifier for these coefficients such that this high probability event holds. Now, in order to write a Chernoff bound, let me just swap the direction of the inequality such that it becomes a small probability event. So the linear combination should be less than or equal to 0 with tiny delta probability. Now, the crucial thing at this point is to think about what it means to actually prove this lemma. So I claim that this lemma is equivalent to bounding the objective of the following max-min optimization problem. So let me explain that to you. Okay, so this max-min optimization problem. So first, we're going to fix an arbitrary pair of bad solutions, this mu hat alpha pair, just fix that. So what remains is we want to minimize this kind of failure probability, right? So this is the objective of the max-min optimization. Now, what remains in terms of quantification, we need to take the worst case overall mean zero variance 1 distribution. Now, because the objective is something we want to be small, if we want to take a worst case, then that corresponds to taking a maximum over the objective. So over all these possible distributions, P. And similarly, the d mu and d alpha coefficients are quantified existentially, meaning that we can choose what we want them to be. So we're going to try to choose them so as to minimize this objective right here. So this optimization problem is completely the same thing as proving this lemma. So what we want to do is to upper bound this objective right here. So this is a really complicated problem because this is, if you think about it, it's essentially an infinite dimensional optimization problem because the space of distributions is infinite dimensional, right? Over the entire real line. So what I'm going to try to do now is to simplify it into something that is finite dimensional using just mathematical programming duality. So that will, at the end, give us something that is tractable and something we can reduce to proving some strange inequality. So that's the goal for the rest of the talk. Okay. So let me start by bounding this max-min optimization by replacing the objective by some upper bound. This is just the Chernoff bound. I've been jumping up and down about getting independence and using a Chernoff bound. So let me actually apply the Chernoff bound. So this failure probability is going to be upper bounded by this object that looks like a moment generating function. It's the expectation of some exponential thing. Okay. So very natural step. The next step we're going to do is actually, we're just going to swap the min and the max. That is a legal thing to do because that's just the standard max-min inequality. You might be wondering now, okay, we're swapping the order of max and min. Does that introduce a lot of slack into the inequality? It turns out it does not, crucially, by a minimax theorem, which is a form of min-max convex concave programming duality. It is actually possible to show that this objective is convex and concave in the corresponding variable such that this inequality is actually an equality. Okay, so that lets me swap the max and the min without sacrificing anything about the optimization problem. Now at this point, let's actually use the independence of this proxy of the estimator, which lets me factor out this n in the exponent. So reduce this n sample moment generating function with a single sample moment generating function raised to the power of n. So after all this rewriting, it doesn't sound like I've actually done much, but after all this rewriting, now the crucial observation is that this inner max is now a linear program, which I'm going to show you on the next slide. This is now a linear program, okay? And the linear program is actually really simple as well. So we're going to have a bunch of variables, p sub x, denoting the probability mass at point x. And implicitly, as we've been assuming throughout the most of the presentation, we assume that the distribution has mean zero and variance 1. Okay, so we're going to optimize over this objective under 3 constraints: that it has unit mass, that the first moment is 0, and that the second moment is 1. And of course, these probability masses have to be non-negative. Now, what about this objective? This objective turns out to also be linear in this p sub x variables, because the expectation of some function is really just the sum of the probability of the quantity being some little x quantity times whatever function it is, right? So this is going to be a linear function in these p sub x variables. Once we have this view of the optimization problem, then we can actually use linear programming duality, which turns, because we've only got 3 primal constraints. This means that in the dual linear program, we only get 3 dual variables. So basically what I've done is turn this infinite dimensional optimization problem with infinitely many variables into something that has only 3 variables. So if we plug it back in, if we plug this back in, this is equal to this optimization problem. We turn from an infinite dimensional min-max optimization problem into a min-min optimization problem with a finite number of dimensions. And that's the purpose of using these mathematical programming duality to turn something complicated into something much simpler. And at this point, this reduces to proving a strange inequality that, again, I'm not going to talk about. But this at least looks tractable. So summarizing, what I've done in the previous step is to use mathematical programming duality to turn a complicated Chernoff analysis into something much simpler. Combined with the very first step, which is finding proxies of the estimator such that we could actually prove Chernoff bounds on them, that essentially completes the analysis modulo this strange inequality that I did not prove. So now really summarizing the entire talk, what I've shown you is an estimator that has sample complexity that is not only big O type, but we actually get the constant type as well. And that estimator can estimate the mean of all finite variance distributions, which contrasts previous works that are either only big O type or need much stronger assumptions. I've also shown you a simple that fits on one slide kind of estimator that is pretty easy to implement as well. And I've shown you two techniques to overcome challenges that's required to analyze this estimator, and hopefully the solutions I talked about are would be useful for your work as well. It's generalizable. In terms of future work, there's still ample work to do, both in the statistical sense and the computational sense. For statistical questions, there's the obvious question of, can we generalize these sort of techniques to doing high dimensional mean estimation? Can we get something that's really tight in high dimensions as well? In terms of computational questions, I mentioned that our estimator is linear time computable, but that's really only assuming that we are working in the usual RAM model. So if all the samples are essentially fit on a single computer. So a very natural question to ask is, can we actually compute our estimator, let's say in a streaming model as well, or maybe if the samples are actually distributed across many different machines. So yeah, with that, let me end the talk right here and see if you have any questions.
So I have a question. Jasper, do you have any intuition of why the, say, the median of means estimator, or just where the non-optimal bound is coming from, the reason why that's happening, and how this correction term?
Yeah, so essentially the median step is the most dodgy part of median mean. It's like taking the median sacrifices constants, essentially. So the median means estimator for the rest of the audience, in case you forget what it is, you take a bunch of samples, you split the samples up into log1 over delta many groups. For each group, you compute the mean of each group. So you end up with log1 over delta many numbers, and you return the median of them. And it's this second median step that seems to typically be sacrificing constants. So here in our estimator, we're really using the independence assumption to get it to be constant type as well.
Can I ask a question?
Yeah, please.
Yeah, can you comment on how to extend this result to the high dimensional setting? Also, another question is that, can you comment a bit on your estimator with the shrinkage estimator in statistics?
Okay, so first question, how do we extend to high dimensions? The answer is we're still looking into it. That's the main answer. But so perhaps let me tell you what doesn't quite work. Like if we try to directly generalize what doesn't quite work. Crucially, in the analysis, we use this psi estimator formulation of the estimator, right? So the thing is, in high dimensions, we're going to end up with a lot of these psi functions. One really tricky thing is that at some point, we also needed to do some discretization plus union bound kind of argument, which doesn't quite work if you have many psi functions with a lot of parameters you're trying to solve the zero for. Essentially, that just wouldn't be tight at all.
Okay, thanks, got it. So is it possible that you carefully quantify the correlation between the new xi's, the new xi's after minusing the alpha term. Like if we, for example, proving the Chernoff bound, if there are some like weak correlation, we can still prove some like Chernoff type bound, right?
Yeah. Right. So the reason why, so there are, of course, even in one dimension, there are lots of like tail bounds for weakly correlated like sums as well. But the reason why we didn't use that is that they typically are either trying to be too general and therefore lose things, or they're really like they need a lot of assumptions, which is why we needed to go through all this machinery that I was talking about in this talk in order to get something that is tight. Like somehow like all the ones I've seen just doesn't seem to work.
Yes, got it. Using that, it's impossible to get the tightest constants.
Yeah, like definitely not in constants, but sometimes not even in the functional, like a bigger form in terms of convergence.
Okay, great. Thanks.
Remind me what your second question was, sorry.
Oh, about the shrinkage estimator, because like for the high dimensional setting, the Gemstein estimator sometimes perform better than the
I see. Yeah. Yeah. I would say that they aren't really comparable, right? Like for one thing, looking at a mean squared error, and we're trying to do a high probability kind of bound. I don't have much intuition about that, actually. Yeah.
Okay, great. Thanks.
Thanks for the question.
Okay, well, I'll stop the recording and take us offline.